Hello everyone. In this video I'm going to talk about belts and pulleys, a very common or a couple of common elements basically in engineering used in lots of different machines. You can see it in your car and in many other places. The goal of a belt and pulley is to transfer power from typically one shaft to another. And so that's not the only mechanism. If you know, we have chain sprockets, we have gears, we have so many other things, right? And so gears are very common for transferring power from one shaft to the other. So you might say, why would you use a pulley, right, with belts? So one of the most important advantages of belts and pulley is transferring power over long distances, okay? If you have a long distance between the two axes, then it's not really an easy job to fill all that distance with a bunch of gears. Okay, it's going to be very expensive, and gears need a lot of maintenance, right? So although gears provide very accurate motion transfer, yet the problem is filling all that gap with gears, which is not economical, and again, a lot of maintenance. The other advantage of belts and pulleys is that since they are elastic and typically they are used over long distances, they basically help with absorbing shocks, okay, and damping out the vibrations, okay? So if there is some vibrations in one of the shafts or one of the pulleys, since they are elastic and over a long distance, the driven pulley is not going to be affected so much by the vibrations in the driver pulley or vice versa. But as I said, the disadvantage is slip, okay, and creep. And so although for two gears, you know that the ratio of the angular velocities, we call the speed ratio, is inversely proportional to the ratio of their diameters. For two pulleys, it's approximately equal to the ratio of those diameters, okay? So it's not really going to be perfectly constant and not perfectly exactly equal to the ratio of the diameters in an inverse manner, okay? So there will be some slip between the pulley and the belt. Now, there are four common types of belts. We have the flat belt, which has a rectangular cross section. We have round ones, we have V ones, and then we have timing ones, which have teeth. Okay, so they look like a rack, basically like a rack gear. And this last one, which is very common when you want motion with precision, with accuracy, this timing belts, like in the cars, they are used. And for them, the type of pulleys that you need is called toothed wheels, like this one, okay? So timing belts are going to be used with wheels that are teeth, and the V ones and the round ones, they are used with the pulleys that are grooved, okay? So grooved pulleys, they have grooves for a V shape, like basically a trapezoidal shape or a circular shape, okay? And then the flat ones are typically used with the pulleys we call crown pulleys, okay? So these are the shapes of the pulleys and the belts that you see in real life, mostly. Okay, the next thing is pulley configurations. So if you want the driver and the driven pulley to rotate in the same direction, you use this configuration, right? You wrap the belt on the exterior of the pulleys. If you do this cross version, right, then this is a reversing system, okay? So this is non-reversing pulleys. This is a reversing pulleys. Here, with this kind of cross configuration, one pulley and the other pulley will rotate in the opposite direction of each other, okay? Or this guy too, if you look at this configuration, this is also basically another one where you have reversing things with two gears in the middle, with two pulleys in the middle. Also, can the axes of the pulleys be non-parallel? Yes. In this case, if you look, the axis of this pulley and this one, which is out of the board, they are in skew situation. Okay, so in this scenario they are skew, and yes, you can also basically have the belt go around like that, and this is really mostly for flat belts, and you can have the axis to be skew. Okay, so these are some configurations for non-inverting, for inverting, non-inverting, inverting, SQ, and other scenarios. Okay. A few other things about pulleys. Sometimes we have a pulley called an idler pulley. So we have a driver one, we have a driven one, and we have an idler one. What's the use of idler? The idler is used when the distance between the two pulleys and the length of this cable don't match. Okay, so you don't want to avoid the center to center distance for the belt that you have chosen, and basically what you do is to make sure that there is tension in the pulley, because as I'll show you in a minute, if there is no initial tension in the belt, there will be no torque transferred from the driver to the driven. So in order to create that, basically somewhere between the two centers, you bring an idler, which is not transferring any power to anything and it's not receiving any power from anything. You just put it there to create the tension, okay? And avoid adjusting the center to center distance. Can I have something like a clutch for pulleys, right? So can I disengage the power in pulleys? Yes. If you look here, this is the driver pulley, and this is the driven pulley, and then you have a loose or an idler pulley. And here you have this shift fork. Then if you move it to the left and the belt sits on the loose pulley, then the power is not transferred to anything. If you shift it back to the right, it comes onto the driven. Now you're transferring what? Power. So you can have a shift fork and a loose pulley next to the driven to have something like a clutch. Finally, as I said, the ratio of these angular velocities, so if you call this one omega 1 and you call this omega 2, omega 1 over omega 2 is approximately equal to d2 over d1. It's not exactly equal to that because of the slip, but it's approximate. Okay, and this is a single number. So is there a chance that I get more than one number? Can I get like a gearbox basically? Can I have several different speed ratios or have variable speed ratio? Yes. So here, if you look here at the bottom, this is a case of something like a manual gearbox, right? Where the driven and the driver pulleys, they have different diameters, and depending on which one of these drums you are engaging with which other one, you can get different speed ratios, right? So your shafts are like step shafts. Or this one where the shafts are not really cylindrical, they are trapezoidal. So depending on where you move again this fork, right, these diameters, these cross sections would change. And so you'll get what? You'll get a continuous change in the speed ratio. And so with both of these, you can get a variable speed, right? Not just one single speed ratio, several. These are like probably 16 separate configurations. This is a continuous one. Okay, next. When you have two pulleys, whether it's in this non-inverting or the inverting configurations, what is the length of the belt that you need if you know the center to center distance and the diameter of the two pulleys if they are given to you, and again center to center, how much of length of the pulley do you need, the belt do you need, and what are the wrap angles around them? Okay, and these wrap angles are important. I'll show you why later on in a minute, but these wrap angles, the angles over which the pulley and the belt have contact, okay, this angle, which here we show for the bigger pulley with theta sub d, and for the smaller one with theta sub lowercase d. So can we find these again as a function of capital D, small d, and c? The answer is yes. Here the formulas are provided to you, And this is the wrap angle for a smaller pulley, the wrap angle for bigger pulley, and this is the length of the belt, the total length. And here, if they are in this inverting situation, in this case, they both will have the same wrapping angle. And again, you'll have what? You'll have the length, and this is the formula for this common wrap angle, and this is the formula for what? For the total length of the belt. And these we can easily find from geometry, right? I mean, you know that the length of this part is what? If this angle theta d is in radians multiplied by d, so that is going to be theta d times d, right? And this portion here, this guy is going to be theta small d times small d, right? The length of the arc is the angle in front of it in radians times a radius, so actually you have to divide by 2, right? So these two are what? These two are the size of those arcs, and then you have this straight line, which is basically that much, right? It comes from a triangle, right? A right triangle. So here, basically, you can form a right triangle, and you can go with something like this, right? Then form a right triangle, and you can find the distance, right? So you have a right triangle, and you can get one side of it, okay? Because this side here is d minus d, right? Of course, divided by 2. And then, again, if this is, let me draw it properly for you. If this is like a, if I draw that for you here, so it is something like this. Okay, this distance is like d over 2. This distance is, or from here to here, this distance is capital D over 2. This distance is c, so that thing over here is d minus d over 2. And in this case, actually, the right triangle is going to be like this. That is going to be the, let me make sure I draw it right. So it is going to be something like this. Okay, so this is the hypotenuse, square it, subtract it from the other one, take a square root, and you should get this one, and you multiply it by 2 to get the total length over here. Okay, so this is how much of belt you need and the wrapping angles, which are important for the next part. Now, what is the next part? The next part is how much tension is in the belt in different parts, and how much power can you transfer between two pulleys given, again, the two diameters d and d, the center to center distance c, from which you can find the wrap angles and L and everything, right? So how much tension is inside the belt? Again, this tension, as we'll see, is not constant. There is a side which has smaller tension, there is a side that has bigger tension, right? And you can see that here, one side we call it the slack side, or the smaller tension. The other side we call tight side, or higher tension. So we want to find how much they are, right? So this one here is called F2, this one here is called F1, right? And you can see them down here in these formulas, right? F1 is the bigger one, F2 is the smaller one, and we want to find them, and then based on this torque that you apply, and then also if these guys are this input gear is pulley, I'm sorry, if the input pulley is rotating at omega RPM, or like n RPM in general, then what is the horsepower transfer between them? Okay, so these calculations are done by somebody called Firbank. So Firbank's formulas are provided here. Let's go over that. So here is an infinitesimal portion of the belt. Okay, so you can see it here. It's a small element of the belt, and there are 5 forces applied on it. Okay, if you draw the free body diagram, there are 5 forces applied on it. There is tension on one side, there is tension on the other side, there is the normal force, there is the force due to rotation, which we call the centrifugal force, and there is, of course, what? The friction force here. Okay, it's static friction, FDN, where F here is the same as static coefficient of friction. Okay, so this F, you might call what? This F, you might call it mu S. Okay, so these 5 forces are there, and the coordinate that we are using here is RT coordinate. So we have the radial direction in this direction, and then perpendicular to that we have the basically transverse direction or tangent direction. Okay, so this is like UR and this is like U theta. And in these directions, we are going to apply some of the forces equal to mass times acceleration, and we're going to derive the equations. Now here, we assume that the mass of the belt per unit length is m. So m here is what? The mass per length of the belt. The width of the belt is b, the thickness is t. So here we assume that the belt is what? The belt is a flat belt. Okay, so it's b by t, and v is the speed of the belt. Okay, and v, now v equals r times omega, or d over 2 times omega, correct, where d is the diameter, or it could be small d, right? And if you want it in RPM, right, then you can also have it in RPM. So if you want it in RPM, then remember omega is in radians per second. If you want to convert RPM to radians per second, you have to do that n, right, and multiply it by 2 pi over 60, and then multiply that by d over 2, so you get n d pi over 60. Okay, so if you want it in RPM, and in RPM, then you can find the velocity of the belt with this formula. Okay, so let's go ahead and apply the equations of equilibrium. So in the radial direction, what do we have? In the radial direction, by the way, since this angle is theta, each one of these forces, F and DF, they are not perfectly aligned theta. If you draw a line here for the theta direction, it should be something like this. Let me see if I can draw it properly, like that. And then these angles, so here you have one angle here and one angle here. Each one of these angles is d theta over 2. Okay, you can see from here too, right? Each one of these is d theta over 2. So when I project F in the radial direction, it's going to be F, right? This vertical component is going to be F times sine of d theta over 2. And since d theta is a small thing, sine of it is equal to the angle itself. So this is going to be approximated by f d theta over what? Over 2. Okay? And that's what you can see over here. And it's downward, so it's in the negative r direction. That f plus df also is downward as well, times sine of d theta over 2, which approximated by d theta over 2. And dn and ds, these two forces, this one and this one, they are in the positive r direction, so we add them and set it equal to 0. Okay, so now this term is a higher order term. It has 2 differentials multiplied. The order of that, the magnitude of that is less than everything else, because all terms, they have 1 d. This guy has 2 d's. So like if these are like 10 to the negative 3, all of these terms are 10 to the negative 3. This guy is 10 to the negative 6. So this one we neglect compared to everything else. Then you have one negative f d theta over 2, another negative f d theta over 2. So it's just going to be negative f d theta. and then dn and ds equal to 0. You keep dn, take these two other terms to the other side, and you'll get this equation. Okay, so this is the result of the equilibrium in the r direction. Then we go what? To the theta direction. For the theta direction, what do we have? For the theta direction, if I go back here, dn and ds are only what? Along r, so they have nothing. But the f and f plus df, they have a theta component, where the component is what? The component is f times cosine of d theta over 2. And again, since this d theta over 2 is very close to 0, we approximate this whole thing by 1. So basically, it's going to be f, and then in the negative direction, and then f plus df in the positive direction. And by the way, you might say, why do you have to add to the f? Why do you have to add the differential to the f? Because f is changing. As we said, f is not constant due to the slip and the creeping of the belt. This tension, as we'll see, is not really constant. So here you see that f plus df minus f, and then of course the friction term, this guy, which is perfectly aligned theta direction, so that's negative f dn equal to 0, and these two f's will cancel. You get simply df equal f dn. Now here, for this dn, you're going to replace it from the top. So you replace it as f d theta minus f ds, and you multiply this friction coefficient by those, so you get this one. Now the term we have to discuss is the ds term, the centrifugal term. The centrifugal term, as you know, for a mass m rotating at the speed of v, or with angular velocity of omega at distance of r, is always what? Is always the mass of the element times r omega squared, right? mr omega squared. That is what you know from dynamics, right? Or you might call it centripetal form. So this is the r omega squared, and this is the mass of the element. Where did you get that one from? Remember, this m is the mass over length. So it has to be multiplied by the length of this element to get the total mass, and the length of this element is, of course, what? Is r times d theta, right? It's an arc. The angle in front of it is d theta, and the radius is r, or d over 2. So the length of the arc is going to be r times d theta. So if you multiply by m, that's the total mass, multiplied by r omega, that's the centrifugal term. If you expand it, it's going to be like this. And remember that r omega is what? Remember, this d over 2 is r. R omega is v. So if you want, you can replace this r omega by v and get it to be this. And here we define this fc term. By the way, this is a term that we're going to see later. This fc is going to be mv squared, okay? Times the theta, or mr omega squared, okay? So this term here, this term, we call it fc. Okay, and let me make sure. Yeah, there is no d theta here. It's just mv squared. This is basically the centrifugal term per length. Okay, this fc is centrifugal term per length. Let me write it for you. Okay, and we'll use this notation of fc later. So ds is what? ds is fc times d theta. So now in this bottom equation, for it we plug in fc times d theta, or for fc, remember it was what? mr omega squared. So you plug it in, so you get this equation here. Good. Now what? Now, if you look at the final equation here, what is the final equation? The final equation is this. It is df equals ff d theta minus fmr squared omega squared d theta. So we divide both sides by a d theta to get this term, then bring this negative term to this side, and keep that other negative term on the other side. So you can rewrite it like this. And what is this? If you look at this, this is a first order differential equation. This is a first order, right? This is a first order ODE, where the goal is f as a function of theta. And the coefficients are constant, as you can see. So the solution of that is very easy. It has a homogeneous solution and a particular solution. So this is the solution for tension in the rope in general, where A is what? A constant. That's the constant of the integration. So how do we determine this A? We need some initial condition for that. So we assume that on the loose side is when theta starts at 0. So when theta starts at 0, the tension on the loose side, we call it F2, F equals F2. So here for F we plug in F2, and for theta we plug in 0. That exponential just becomes A. So it becomes F2 equals A plus what? Mr squared omega squared. And if you swap A and F2, you'll get the value of the constant. So that constant is F2, the tension in the, basically we call the loose side, right? Or here, if you remember, we called it what? We called it the slack side. That's equal to that. And then what? Minus m or omega squared. And let me show you that over here too. So this is the pulley, and this is basically the direction of torque that is applied on the driven pulley. And this is the slack side. This is what? The tight side. And at theta equals 0 here, F equals F2. At theta equal phi, where phi is the entire wrap angle, F equals what? F1. And then between these two, F is constantly what? Changing, okay? So we found the constant. We can plug it back here now. And then your F equation becomes like this. So this is your F equation now as a function of theta. Now we say, as I said, on the other side, where theta becomes the wrap angle phi, F becomes F1. So we plug in for theta phi, and for F we plug in F1, and you'll get this relation here. And now what I'll do is I'll bring that mr omega squared to the left side. So it becomes F1 minus r squared omega squared, and then divide both sides by this. So it becomes F1 minus the Fc over F2 minus Fc equals what? Exponential of F times phi. And this very important equation we call belting equation. Okay, and this equation, if you look at my lecture on statics for tension in the rope, I have on the channel where I said, is tension in the rope constant? No, it's not. If you remember over there when we talked about the static scenario, we had a formula. If you remember it, it was F1 over F2, or T1 over T2. In that case, it was E to the mu times alpha, right? This is the formula that we had in the static scenario. This is exactly this, where what? Where alpha is the same as phi and mu is the same as F. And the only thing we don't have in the static case are rotations. So these guys, if you set them to 0, then you'll see you'll exactly get what we had in statics. So that statics equation that we had is a special case of this equation, which is the dynamic equation. So in the dynamic equation, the difference between the tensions and what? The centrifugal force per length, per length, that is equal to exponential of mu times alpha, or in this case, F times phi. Okay, so this is an extremely important equation called belting equation. Okay, now let's look at the last part. So here, remember that initially we have to have tension, initial tension, in the ropes in order to be able to transfer torque. So let's look at that and formulation of that. So in this case, it's the exact same thing as before with a little bit modification. So in this case, okay, I want to show you that basically on one side you will have F1 is going to be Fi plus Fc plus T over D. On the other side, F2 is going to be Fi plus Fc minus T over D, where T is the applied torque or the transfer torque. Fi is the initial tension, and Fc is that same what? That same centrifugal force. Okay? And clearly you see again F1 is bigger than F2, right? So these are going to be the formulas directly for F1 and F2 if we also add the initial tension, which we should. So let me show you what happens here. Okay, so here clearly F1 minus F2 equals T over D over 2. What is this? Well, here if I multiply both sides by a D over 2, you'll get D over 2, which is R, times F1 minus F2 equals T, and this is simply the torque calculated based on the torque of the F1 minus the torque of F2, and of course they are in opposite directions, so you have to subtract. Okay, so this relation that F1 minus F2 equals T over D over 2 or 2T over D, this is obvious. This is the balance of the torques, right? Yes? Good. Now in this case, if you add F1 and F2 together, this T minus T and T plus T would cancel, so you simply get 2Fi plus 2Fc. From here, you can calculate Fi. Fi is going to be F1 plus F2 over 2 minus Fc. Yes? And now I'm going to divide 1 by 2. Look here, I have Fi here, and I have T over D. Look. Here I have T over D. T over D is what? It's basically T over D is, if I get rid of that 2 and bring it here, T over D is 2F1 minus F2. And Fi is F1 plus F2 over 2 minus Fc. If I divide 2 by 1, in this case I said 1 and 2, you can say if you want 2 divided by 1, you can find Fi over T over D is this. If you simplify it and from here you find Fi, you can get what? You can get this relation. Now you might say, where did you get this one from? Well, here, if you look here, what do I have? Okay, let's multiply both numerator and denominator of this by a 2. What would you get if you multiply both by a 2? It's going to be F1 plus F2, yes, minus 2Fc divided by what? F1 minus F2, yes? Good. Now what is this? Can I find it from anywhere? Yes. Where does it come from? Well, let's go back and see. Here I had F1 minus Fc over F2 minus Fc is what? Is this, right? And from here, if I plug it back into this, right, then I get this equation. So from here, you get this very critical equation here. The amount of the initial tension you need in the belt. How much is it? T over D exponential of Fi plus 1 over exponential of Fi minus 1. This is the required what? This is the required initial tension. If you don't have this much tension in the belt in the beginning, you will not be able to transfer what? Torque. So this formula is very critically important, okay? And let's talk about the meaning of this equation. So the first one, as I said, is what? if you want to transfer torque, you need to have Fi. If Fi is 0, T is 0. So no initial tension means no torque transmitted. 2, the torque that you transfer is in proportion to the initial tension, and you can see it from here. You can see that Fi and T, they have a linear relation to each other. So if I make the initial tension 2 times bigger, then I can basically transfer 2 times more torque. Okay, so if you want a satisfactory flat belt drive, not only you have to provide the required initial tension, you have to sustain it in the proper amount provided by the formula and make sure it's maintained. So you have to check it once in a while and make sure the tension in the rope is sufficient so it can transfer the amount of torque. Okay, so this formula here is one of the very most important formulas. And where do I get phi from? Well, remember the phi here is one of these two, right? The phi is one of these two, depending on whether the small one is the driver or whether the big one is the driver. So one of these two is going to be what? Your phi. Good? Okay, the last part. So can I find F1 and F2 individually? Because so far what I found was the ratio between F1 and F2 related to that exponential term and Fc. Can I find individual terms? The answer is yes. How can I do it? Well, all I need to do is go back to the formulas that we had for F1 and F2. Remember, F1 is Fi plus Fc plus T over D, right? Yes? This is the formula for it. And now what I need to do is the formula I found for Fi, which is this guy, I'm going to bring it and plug it right here. And if I rearrange it, all you will see is basically going to be what? Going to be in terms of only Fi and Fc, right? And you might say, did you plug in Fi here? No. What I found T over D from this formula in terms of Fi and then replaced it. So if I factor this out, this is going to be the formula for the maximum tension. This is going to be the formula for minimum tension. Okay, and these formulas are very important. So this is what? This is the max tension, and this is very important again. The minimum tension is not so critical, but the maximum one is, because each belt has a rated tension that it can tolerate based on the material and the cross section. So if the tension in a belt, the maximum passes this amount of rated tension, then you'll have the belt be ripped apart. Okay, so this is another extremely important formula, this formula for F1. This is one, the other one is Fi, and finally, and you see here F2 is calculated in a similar manner. Finally, you can find the horsepower. You know the horsepower, the power in general is what? The power, if you remember, is torque times omega. Okay, that's the power transmitted. And for T, I have a formula for T. Remember, I can find it from this equation. I can find T, right? And it is going to be in terms of what? The T is, look here, I can find T from here. That's the simplest thing you can do. Remember, T is what? T is D over 2 times what? F1 minus F2, yes? So that's what you can see here, F1 minus F2. Now, here, D over 2 is basically what? So this is like F1 minus F2 over 2 times D. And this D over 2 times omega is basically that velocity that you can see. Then you might say, where does this 33,000 come from? Well, here the unit of H is not in watts, it's horsepower. Okay, so if you want it in watts, then you use this formula. Use what? If you want it in watts, then you simply say F1 minus F2 times what? Times V. That's what you say. If you want it in horsepower, then you can use the top formula. Okay, so this is another very important formula, how much horsepower it can pass, which is basically the same as the torque formula. So three major things. This is how much horsepower you can transfer or how much torque you can transfer equivalently. And this is the initial tension you need to make it happen. And this is the maximum tension you will have in the entire belt, using which you can design the belt. And in a separate video, I'll talk about the design of the belt or selection of the belt if you want. But this video is getting too long, so I will stop it right here. And in a separate video, I'll talk about design or selection of the belt. So I'll stop it here. This is mostly about basics of the belts and pulleys. Hopefully this video was useful to you. I'll see you in the next lecture. Thank you.